All right, today's lesson is over the Lagrange error bound 9.7b. Uh, Now, error bound is used in the same conversation as when we were talking about remainders. So just a bit of background here. If we're trying to approximate the sum of a function using polynomials or series, and we don't get the exact answer, we can ask how far we are off from that sum. In other words, how close is my approximation to the actual sum? And even if we can't find the actual sum, there is a way to find out how close we are to that actual sum, hence the remainder and hence the error bound. Now, recalling what we've studied in the previous section is alternating series remainder. So just to kind of recap alternating series remainder, which we're going to see some very similar setup from that last section. Suppose an alternating series. So we know alternating series is one that oscillates between, each term oscillates between positive and negative values. So let's say we have a converging alternating series and it passes the alternating series test. If the series has a sum s, and that sum s is the actual sum of that series, then the remainder is going to be the absolute value of the actual sum minus the polynomial approximation, s sub n, the partial sum. And the absolute value of that is going to be less than or equal to a sub n plus 1. And what that means is that the maximum error for the nth term, partial sum s sub n, is no greater than the absolute value of the first unused term, a sub n plus 1. So what we found with alternating series, as long as that series is converging, then we know that whatever partial sum, let's say s sub 5, we know that s sub 5 is no, the maximum error for that polynomial is no greater than the sixth term, the first unused term. And if we look at this diagram, we can kind of see that if we have the actual sum of a function, then we see that as we increase the partial sum, s sub 1, s sub 2, s sub 3, s sub 4, we see that the sum is going to get close, it's going to oscillate between above and below the actual sum, but it will get closer and closer to it. And so we know that the following term will be will produce the worst case scenario for the error or for the remainder. Okay, so that ties in a lot with what we're going to talk about with Lagrange error. So when a Taylor polynomial is used to approximate a function, we need to find a way to see how accurately that polynomial approximates the function. So let's say we know that a function is simply the polynomial approximation plus however much off that polynomial is from the actual function, which is represented by this remainder. And if we rearrange this equation, we can simply say that the remainder, therefore, the nth term remainder, is going to be the actual function minus the polynomial or the partial sum. Now, written in words, we can say the function is equal to the polynomial approximation plus remainder. And again, if we rearrange the equation using words, remainder is simply the function minus the polynomial approximation. Okay, so this is actually the Lagrange error bound, but let me just, let's kind of recap a bit of what we've seen with the Taylor's theorem. Now, Taylor's theorem, we know we've seen this pattern, right? F of x is f of c plus f prime, x minus c, and then we keep increasing the derivative, but then we also divide it by the n factorial times x minus c to the n plus 1. and then we keep on so on and so forth until we get to the nth term, right? The f, evaluate at the nth derivative, evaluate at c over n factorial times x minus c to the n. So this is the polynomial approximation with this being the last term. So if this is the last term, then we can actually use the first unused term to represent the remainder. So the first unused term will simply be taking the n and just increasing that by 1. So if we take the first unused term, it'll be f of n plus 1 evaluated at z over, it was n factorial, but now it becomes n plus 1 factorial, x minus c, it was n, but the first unused term will be represented by n plus 1. Now the only thing that is different here is that we are not completely sure, or we are kind of in the dark as to what this z value is, right? However, we do know that this z value has to sit somewhere between x and c to produce the exact remainder that the polynomial approximation is off by. So the thing is that we're not going to know this exact value of z, but it's okay because all we need to do is, if we can find a worst case scenario, if we can pick a z value that will cause this expression to be as large as possible, and I used this notation to indicate that, then we're going to be safe. We're going to know that the remainder cannot be any greater than this maximum value that we've created. Okay. So if we want to find the error of any polynomial approximation, we can simply go to the first unused term, and we do have to do a little bit of work trying to maximize, trying to find the maximum, trying to pick the appropriate z value that will maximize this expression. But once we do that, then we can just basically follow this form to help us produce a remainder that will be a safe upper bound for our function. Okay, let's go to the back page. So a bit more about this remainder error bound. When applying Taylor's formula or this Lagrange error bound, we will not be expected to be able to find the exact value of z because the exact value of z will be the value that will be producing the exact remainder. Okay, we're not going to be able to find the exact remainder. If we could find this, then approximation would not be necessary. Rather, we are merely interested in finding a safe upper bound, a maximum value for this for this expression here, and we're going to simply choose a z value that's going to sit between x and c, from which we'll be able to tell how large the remainder is. Now we want to maximize this n plus first derivative on the interval from x to c or from c to x. And the maximum error bound is again the worst case scenario for the interval in which our actual approximation can live. So let's look at example 1, and as we go through example 1, I will keep referencing back to this formula that we're going to be using. Okay, so example 1, let f be a function with 5 derivatives on the interval from 2 to 3, 2 comma 3. Assume that the 5th derivative evaluated at x is less than 0.2 for all of x in the interval from 2 to 3, and that a 4th degree Taylor polynomial for f at c equals 2 is used to estimate f of 3. How accurate is this approximation? Give 3 decimal places. Well, basically, if we want to find out how accurate the approximation is, we need to figure out what the remainder or what the error is. So we're going to be evaluating, we're going to use this formula, and we're going to plug in the n, the x, and then we'll go from there. So we know that this is a 4th degree Taylor polynomial. So we know that therefore this is talking about the n value of 4. So we're going to replace this n with 4. So it will be r sub 4. But the x value that we're going to approximate is going to be f of 3. So therefore this x will be replaced by 3. So we're going to evaluate the fourth degree polynomial, the remainder of the fourth degree polynomial, evaluate at the x value of 3 is equal to f of, now we know that if n is 4, then we know that n plus 1 must be 5, right? Anytime we're talking about error or remainder, we're always going to be involving the first unused term or the first omitted term. So if this is the fourth degree polynomial, then this will be 5. If this is a fifth degree polynomial, then we know this must be 6. Okay. Evaluate z again. We don't know what z is, so we'll come back to that. X minus c. So x we know is 3 because used to estimate f of 3 minus c. Now we know the center. They tell us the center is at 2. So 3 minus 2 raised to the n plus 1, which is 5. So all we're doing is we're just looking at the formula and we're just simply replacing the n and the x and the c with the appropriate values. And we're leaving that z alone for now. Now we don't know what z is. However, we do know that this expression can not be any greater than this value, 0.2. All right. No matter what z is, we know that any value. We know that z has to sit between x and c. So no matter where it can be, this expression has to fall under this value of 0.2. So we know therefore this is the worst case scenario, right? So this worst case scenario, we can think of this as the max value. So we just know that this must be less than 0.2. So if we just replace that with 0.2, then we have a safe upper bound to work with, knowing that the remainder cannot be any greater than this. So 0.2 over 5 factorial. 3 minus 2 is 1. 1 to the 5th is 1. So if we plug this in the calculator, we know that the remainder has to be less than 0.00166. So what therefore is saying is that this fourth degree Taylor polynomial is not going to be the exact, it's only going to be an approximation of the actual function. However, even though this is just a fourth degree Taylor polynomial, it is at worst only off by 0.00166. So even though this is only a fourth degree Taylor polynomial, we already see that it is already pretty accurate. Okay, so suppose that the fourth degree polynomial evaluated at 3 is equal to 1.763. Use your answer to A to find an interval in which f of 3 must reside. So what this is saying is that we know that the fourth degree polynomial evaluated at 3 is 1.763. Okay. However, we know there's only an approximation, and this approximation is going to be a value that's going to be at most off by 0.00166. So therefore, we can think of it as we take this approximation and we just give or take this remainder or this error. So we know that f of 3 must sit somewhere between 1.763 minus 0.00166, or at most it'll be 1.763 plus this error, right? We know it's gonna be at most off by 0.00166. So we just take the approximation and we subtract this value and then we add that value, and then now we have a range as to where this f of 3 must reside. So we know f of 3 must sit between 1.7613 and 1.76466. Okay. Now on to the next question here. Could f of 3 equal to 1.778? Well, 1.778, we see that is outside of this interval. So therefore, we know it can't be 1.778 because we know that at worst, this approximation is only going to be off by 0.00166. And we know, so therefore, we know our approximation cannot be above or below these two values. Okay, and then, so no, since 1.778 is outside the interval, could f of 3 equal to 1.764? Now, 1.764 does fall between these upper and lower bounds. So therefore, yes, since 1.764 is within our interval. Okay, example 2. All right, find the fifth degree Maclaurin polynomial for sine of x. Then use your polynomial approximation to approximate sine of 1. And use Taylor's theorem to find the maximum error for your approximation. Give 3 decimal places. Well, we should have memorized the Maclaurin polynomial for sine of x. We know sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So if we're going to use this to approximate sine of 1, we're going to simply replace all the x's with 1. 1 minus 1 over 3 factorial plus 1 over 5 factorial. It says to find the fifth degree Maclaurin polynomial. So as soon as we reach the fifth degree, we stop. Okay, so here there's only 3 terms, but we stop here because that is this is asking about the fifth degree Taylor polynomial. So once the exponent matches the degree, then we don't continue with the Maclaurin polynomial or Maclaurin series. Now, using our calculator, we can plug this in, and we're going to see that this sine of 1 is going to be approximated by this value of 0.8416. Now, 0.8416 is only approximation, so we want to figure out, at worst, how far are we off from the actual polynomial, from the actual sine of x evaluated at 1. Okay, so again, we're going to refer back to our Lagrange error bound, and we're going to evaluate this remainder, fifth degree, evaluated at 1. Okay, so our remainder of this fifth degree polynomial evaluated at 1, we know that we're going to involve the first unused n term. So we're going to involve the sixth degree polynomial, evaluate at z. Instead of 5, we know it's going to be n plus 1, so 6 factorial. X minus c, so we know it's going to be 1 minus 0. 1 because that's the x value. We know the center is at 0 because the Maclaurin series has a center of 0. So 1 minus 0. Again, we have to increase the n plus 1 to be 6. So n is 5 in this case, so that's why all the n plus 1 in this case will be 6. All right, so now once there, we know that f of 6 evaluated at z. Let's think about worst case scenario. What is the largest or the smallest or largest value that this sine curve can take on? Well, if we think of a sine curve, we see that it's going to oscillate between the y values of -1 and 1. But we're only asking for the absolute value, right? We see the absolute value here. We see the absolute value up here. So we know that this is not going to be any larger than 1 because of what we know about the sine curve and its characteristics. So we know that this cannot be, even though we don't know the value of z, we can think of this as the worst case scenario. We know this cannot be any larger than 1. So we're going to put that upper bound being 1. And then we're going to just evaluate the rest of this. 6 factorial, plug in the calculator. 1 to the 6 is simply 1, so 1 over 6 factorial is 0.00138. So this approximation cannot be off more than this error. Okay. So if that's the case, then we know that the actual value must sit somewhere between 0.8416 subtracted by this value and the upper bound being 0.8416 plus this error. So once I do 0.8416 minus the error, I get 0.84027. And when I take this and add the maximum error, I get 0.84305. So we know the actual sign of 1 must sit somewhere between these two values because we know the approximation and we know the error. So then part C, it says, could sine of 1 equal to 0.9? Why or why not? Well, we know sine of 1 must sit between 0.840 and 0.843, so 0.9 is outside this range. So therefore, we can say that 0.9, there's from what we have found, 0.9 cannot be the value for sine of 1.